All right. So when it comes to the rational functions and the asymptotes, they work together. They work together because without the asymptote, the rational function doesn't really know where to start to curve, right? So it sets up a boundary in essence where the curve cannot cross the asymptote, right? It can get really close to it and infinitely close to it, but it just can never touch it. So there will never be an intersection between the asymptote and the curve. So every rational function has a horizontal asymptote and a vertical asymptote, all right? They have both, every one, all right? So there's a little bit of a definition there and to give you an idea of, what they are, all right? What I wanted to point out especially is take a look at the way that the rational function is written, right? You see it as f of x is equal to a. A is in the numerator by itself. All over in your denominator, you have the x minus h, right? So I'm looking at this part right here. And then at the end of the fraction, you see plus k, right? So h is in the denominator. H is what tells you to shift the function left or right. And then you have k, which tells you how to shift the function up and down. A will still be the determining factor as to whether you will compress, stretch, or reflect, okay? So A still controls the same things that it controlled in all of the previous functions. It's just that it looks slightly different. A is in the numerator, and you have your x, your variable, in the denominator, and that's what makes this the rational function. Having the variable in the denominator, or having the x in the denominator, is what gives us this rational function, okay? Any questions on that so far? So the unique thing is that there isn't really a vertex when it comes to rational functions. What there is like what we call, it's down here actually, let me see. It's called like the center of the hyperbola. But that isn't really all that useful to us necessarily. So the one thing that rational functions we don't really discuss is this idea of a vertex or a starting point. Okay, because the curves are kind of split up, there's really nowhere where we can identify as like, okay, this is the starting point. If anything, what it does is it just tells us where we shift the asymptotes. Okay, so we'll kind of get into that. So square roots do have a starting point, but rational functions don't. So if you're talking about homework from Sunday, I hadn't uploaded this homework because I did this one last night. So square root functions have a starting point, quadratics have a vertex, absolute value has a vertex. I'll have to look at it. Maybe that was a mistake of mine, but there shouldn't be, there is no vertex when it comes to rational functions. All right, so let's begin. There's a lot to cover, so I know you guys have questions. Hopefully I can get to them by the end. Okay, so the first thing is the parent function, right? So the parent function is essentially the function with no shifts, no stretching, no compression, no reflections, right? So I want you to consider this function, the f of x is 1 over x. This one down here is like saying add nothing to the denominator. And then you also have nothing, right, plus 0 as your k value. All right. So what does that mean? Well, it tells us where the vertical asymptote and the horizontal asymptote are going to be as well. All right, so the H value, which typically is the one that we would see down here, well, that one's 0, okay? This one tells you where your vertical asymptote will be. So there's a relationship between the H value and then the vertical asymptote. So the vertical asymptote is a line that's vertical. So then your vertical asymptote would occur at x equals 0. All right, this is a vertical line. So what you would see is this line right here. And we would label this. You could label it as VA, vertical asymptote, x equals 0. The horizontal asymptote comes from the shifting up and down. So if there is no shift up or down, then that tells you that the horizontal asymptote will stay on the x-axis. All right, so this one tells you horizontal asymptote. All right, so then this one is the other variable. It'll be y equals 0. Okay, and this would be a horizontal line. So then what you get is this right here. Yeah, basically. And this one you can label as HA for horizontal asymptote, y equals 0. Okay. Now, without getting too far into the sketching and the curves, all right, the rational function exists in quadrant 1 and quadrant 3. Okay, the one point that I do know is 1, 1, and it creates a curve like this. The other one is down here at -1, -1, and it creates a curve like this. Okay, I'm only sketching it out quickly because what I want you to look at is the domain and the range. All right, let me see. Wait, mister, if there was a -2 as the vertical asymptote, would it stay the same? Or is it a negative, or is it the opposite? If it was a -2 as the vertical asymptote, then if it was like 1 over x minus 2, is that what you mean? And then your vertical asymptote would be your h value. In this case, your h value is opposite of -2. So then you would have a vertical asymptote at x equals 2. All right, we'll talk about that because we'll have an example later on. All right, so if we sketch out the graph quickly, the whole point of doing that is I want you to see the domain and the range, okay? The reason why the asymptotes are so important is because here the curve never gets to actually be 0. We never have the opportunity for x to be 0, because if you did, if you go back to this original function, imagine what would happen if x was 0. You would have 1 over 0. And what is 1 over 0? No, it's not 0. You can't divide by 0. No, it's not nothing. It's something that we call undefined. Okay, it's called undefined. There is no value. It's not possible to divide by 0. If you try doing it in a calculator, what you get is like syntax error, or you get something different. Okay, but you just cannot have an answer when you divide by 0. So what does that mean in terms of the domain? Well, then if I'm looking at these green curves, I can see that the green tends to cover pretty much everything along the x-axis, but the only number that x cannot be is 0. And that's why the vertical asymptote exists there. That at x is equal to 0, and you see it right here, when x is equal to 0, I won't have a solution. I will be undefined. So then how is the domain related to the vertical asymptote? Well, basically, the vertical asymptote tells you the one number that the domain cannot be. All right. So for rational functions, we have a new way of writing domain that is a little bit simpler than what we had before. All right. The domain, what it's going to be is it's going to be a set. So it's a curvy bracket, right? So the domain means the set of all x values, a vertical bar, and that means all x such that x does not equal 0. All right. We are saying that our function has a domain of all real numbers except for 0. Yeah, it's kind of like the IXL. The curve represents a set. So when you have the curved brackets, it means it's a set of numbers. In this case, it means the set of numbers that x, right, the set of all x such that. So this little line right here represents such that. You would close it. You would close it. In this case, it's not like an open and close situation because you're doing a different notation. You're doing a curved bracket. So if you open with a curved bracket, it closes with a curved bracket. So what you're saying here is all x values, as long as x is not 0. That's the only number that's going to cause a problem. All right. So vertical asymptote and domain are related. Okay. And then horizontal asymptote and range are related, right? So if I have an asymptote at y equals 0, what do you think my range is going to look like? Correct. It's backwards now because it's easier to think of what we can exclude instead of what we can include, right? It's easier to say everything except 0 rather than the other way around, because then you would have to have an interval notation, union, another interval notation. I think that this way is a little bit cleaner. It's simpler. Yeah. So all numbers except for 0. The line, you mean this line right here? So the line just means such that, all x such that, or all x as long as. So it translates into such that, or it translates into as long as. Okay, so all x as long as x does not equal 0. Okay, and then for the range, you take a look at what was the horizontal asymptote. Well, in this case, the horizontal asymptote was y equals 0. So then it's pretty much the same thing, except that for range, you're talking about the y values. So for range, you're going to say the set of all y values such that y does not equal 0, and you're going to close it with the curved bracket. So I want to get this idea across. When you do set notation, which is what this is set notation. This is not interval notation. With interval notation, you use open and close. So you use parentheses and brackets. When you start a set, you open with a curved bracket and you close with a curved bracket every time. Okay, so it's a notation that just means everything that's inside my set is good, except for the one number that we are excluding. Correct. It's basically saying any number as long as it's not 0. That is correct. All right. So that's how the asymptotes are related to the domain and the range. So typically, if you can find the asymptotes first, it tells you what number cannot be in the domain and it tells you what number cannot be in the range. It is the same number that your asymptote is. Okay, so the domain can't be 0 because I have a vertical line at 0, and my range can't be a 0 because, or range has to be excluded. 0 must be excluded from the range because there is a horizontal line at 0 as well, a horizontal asymptote at 0. Okay. So somebody was asking earlier, like, what is the vertex of like a function like this? There is no vertex, but what we do have is kind of like what we call the center of the hyperbola. The center of the hyperbola happens here, where the two asymptotes intersect. So that point would be 0, 0, right? But that point is not as important to us, especially because we're not graphing these. All right, so that would be my center. Okay, the center would be 0, 0, because that's where the two asymptotes intersect. As far as the 1, 1, this point right here, I just knew that because that comes from the parent graph, right? When x is 1, the output is 1. So I knew that. I put that point there just so I could quickly sketch out the curve. 0, 0 is not the starting point. No, 0, 0 is the center of the hyperbola. It is where the two asymptotes intersect. But the function never goes to 0, 0. Okay, this here is to the center of hyperbola. Okay, we're talking about the point 0, 0, because that's where the asymptotes intersect each other. Oh, am I going to ask where the asymptotes intercept? Not likely, not likely. Okay, I would if we would have been able to graph these, right? If we had time to learn how to graph them, then I would have. But since I'm not going to ask you to graph anything, then the center of the hyperbola is not as important. Okay, what's more important is understanding how the asymptotes work, how they affect the domain and range, and then knowing how to find the intercepts of these functions. Okay. Will they ever intersect? What will ever intersect? Are you talking about the two curves? No, the two curves will not intersect. They're moving in opposite directions of each other, so there is no point where they will intersect with each other. All right, so now let me move on. In general now, right, in general, the center of the hyperbola will be u as h comma k. All right, so in the parent function, since you had 0 for h and 0 for k, you ended up with a center of 0, 0, right? But if you have a shifting going on in the horizontal or vertical direction, then the center of your hyperbola will shift with it, okay? So very much kind of like a vertex. So you see what I'm saying? Like it's kind of like a vertex, but not really. It just tells you the center of the hyperbola where the two asymptotes are crossing each other, okay? The vertical asymptote is x equal to your h value. Your horizontal asymptote will be y equal to your k value. All right. So this is in general. All right. This will be in general. That's the general rule. So when you look at a rational function and you want to know, okay, like, what is the to be, I look at my h value. If I want to know the horizontal asymptote, I look for the k value. Any questions so far? All right, so now let's go ahead and let's take a look at a function where some transformations have taken place. Okay, so this will be your first example that you would have to write down. We're going to find each one of these things. So we'll start with transformations. We'll find vertical, we'll state domain. We'll find horizontal asymptote. Then we'll state the range. And then we'll move on to the final part, which is to find the X and the Y-intercept of the rational functions. You're going to write this down on your notebook. Yeah, I will post the video. There should only be, you're only going to create 4 boxes. We only have 2 examples. So on one side, I'm doing like asymptotes and domain and range. And then on the other side, I'm doing the intercepts. Okay, so that way you have enough space to fit everything. Four boxes, that's correct. Let's resume. All right, so let's begin with the transformations. Right now, we don't have many, okay? There's only 2. I want you to notice, first of all, A is what's gonna be in your numerator, right? So that A value is 1. So that hasn't changed for the parent function, all right? You have X in the denominator where it's supposed to be, all right? So what can you tell me? What can you identify as horizontal shifts that are taking, I'm sorry. What can you identify as transformations taking place right now? All right, so we have one that would say horizontal shift 5 units right. Okay, so think about it, right? You have your parent function and you're shifting everything to the right. So where is your vertical asymptote going to end up? It's going to end up, if I'm shifting 5 to the right, yeah, it would be at X equals 5. Okay, this is where my vertical asymptote would be. Right? So at 5, vertical line, so you would have X equals 5. All right, and then that's how you can easily get your vertical asymptote. Okay, someone mentioned a vertical compression by a factor of 1. Well, if A is 1 already, I am only a compression if I'm smaller than 1. So if the parent function starts with 1, and I'm at 1 right now, nothing has happened. There is no stretch or compression. It would be a stretch if there was like a 2 or a 3 or a 4, something bigger than 1. But if I go from 1 to 1, nothing happened. There's no stretch, no compression. So what else would I say? What other transformation is taking place? Okay, so we would have just a vertical shift instead. Right, vertical shift, which again, just a reminder, the vertical shift should be described last. Vertical shift, 3 units up. Okay, so now I've shifted not only 5 to the right, so you can see how that vertical line shifted 5 to the right, but now think of the horizontal asymptote, which was at 0. Now you have a vertical shift 3 units up. So then where is the, there you go, right? Where is the horizontal asymptote? The horizontal asymptote would be at Y equals positive 3. Right, so imagine the horizontal line at 3 going all the way across. That's where your horizontal asymptote is at. All right, so you identify the transformations as you go, right? You can utilize them to help you identify where those asymptotes are going to be, all right? And then you can use those asymptotes to help you determine, well, what is the domain looking like, okay? So if we had to exclude one number from the domain, what number would it have to be? I would want to say it's the set of all X such that X does not equal which number? Yeah, you don't want 5 to be in the domain. Why is that? Well, imagine if this number was 5 and you would have 5 minus 5 in the denominator. Now you end up with 1 over 0. And 1 over 0 is undefined. And if you add 3 to an undefined number, it's still undefined. So that's why we want to keep 5 out of the domain, because it does not allow us to get a output. It does not allow us to have a real output. So the domain is all x such that x does not equal 5. Okay. With the first function, I didn't want 0 because the only piece in my function was x. So you need to be careful with what you say cannot be in the domain. Here, I can have 0. X can be 0 because 0 minus 5 is negative 5, and that's okay. That's not undefined. It's only a problem if the number that you plug in turns the denominator into a 0. Okay, so in this particular function, you could plug in 0, you won't have a problem. But if you plugged in 5, then you have a problem. All right, for the range, similarly, right? Look at the horizontal asymptote. The horizontal asymptote is at 3. So the one value along the y-axis that you can't reach is 3. So your range would be all y such y does not equal negative 3. All right, so transformations, asymptotes, and domain and range are all kind of related on these rational function problems, okay, which makes them kind of nice, all right? Oh, I'm sorry, you're right. I wrote that wrong. Y cannot equal positive 3. Any questions up until this point? I miswrote. It should not have been negative 3. It's supposed to be positive 3 because we're only excluding this number, which is where the horizontal asymptote is at. Okay, does that make sense? If it was plus 5, what would the domain be? Well, if you would have had this instead, if it would have been x plus 5, then that means the vertical asymptote would have been x equals negative 5. So that means that the domain could not be, x could not be negative 5. So it's the opposite, right? Since h is always opposite, we would read the opposite value. So you would exclude negative 5 instead. Okay, does that answer your question? Correct. Yeah, h is opposite, k is keep, just like all the other functions. All right, sounds good. All right, let's move on over to the X-Intercepts. You guys kind of know the process for this. It's the same as before. It's just how do you handle it with a new type of function, right? So we have an X-Intercept. We want to solve for X-Intercept. This is where you want to set your y equal to 0, all right? We know that we would have to turn the f of x into y. So we have y equals 1 over x minus 5 plus 3. So I'm going to turn y equals y into 0. So I have 1 over x minus 5 plus 3. Here's what you're going to do first. You're going to move the constant 3 to the other side. All right. You're going to want to get that fraction by itself. So first subtract 3 from both sides. And what you're left with is negative 3 is equal to 1 over x minus 5. All right. I want you to treat the denominator as one factor, meaning that it's an expression that is basically stuck together. X minus 5 is one piece, one expression. What you're going to do here is you're going to do cross multiplication. All right. It's a strategy that helps you remove any denominators from the equation. Okay. But what you would need first is give the -3 a denominator of 1. Then it allows you to cross multiply. All right, so some of you might know this as you might know this as like butterfly method. It is kind of like a fraction buster, but not really, because what you're not multiplying by a constant number, you're multiplying by an expression. So I don't want to confuse the two different methods that we have. Fraction buster is when you're trying to get rid of a fraction that's just like a whole number. Here we're trying to get x minus 5 out of the denominator. All right, so here's what you're going to multiply. You're going to multiply -3 with the expression x minus 5. All right, what does that look like? Well, that becomes -3 times x minus 5. You want to write it that way, okay? And what is it going to equal? Well, then it's going to equal 1 times 1. Now you multiply these two together. Okay, so it equals 1. All right, I'm sure you've probably seen this at some point. Okay. So then multiply here, you get -3x. -3 times -5 is +15 equal to 1. So then from here, you would subtract 15. -3x is equal to -14. And then you divide both sides by -3. So what you're getting is x is equal to 14 over 3. All right. That would be the x value of the intercept. Now, I continue to see this mistake on like tests and quizzes that you're giving me the value of x only, but you're not answering the question, which is what is the x-intercept? The x-intercept must be written as a coordinate point, okay? So the coordinate point for this would be 14 over 3, comma 0. This is the solution that I should see. A lot of you are just giving me this, and I've been kind of like, you know, trying not to take off any points for that, but you need to remember that this should be represented as a coordinate. All right. Other teachers will be a lot more picky, like I typically am, but over distance, you know what I mean? I'm trying to give you a little bit of a break. So I need you to remember that when you get the x value, it becomes a coordinate, right? Where on the graph do you see it crossing the x-axis at the point 14 over 3, comma 0? Okay, that's where you see it. All right, so please remember that. I will always prefer it in the fraction form. You'll see work from you having to turn it into the decimal form. So please leave it as fraction form. All right, and then we look at the Y-intercept. All right, let's take a look at the Y-intercept. So here we want to plug in the 0 for x. Okay, so what we have is y equals 1 over 0 minus 5, and then plus 3. So in this case, you just clean it up as much as you can. Right? You're going to get y is equal to 1 over -5 plus 3. 1 over -5 is the same thing as -1 over 5. It's just -1/5. Okay, that's all it is. And you're adding 3 to that. Okay, so I want to get a common denominator here. I know that the denominator I want it to be is a 5. So I'm going to multiply top and bottom by 5. So then that allows me to add 15 over 5. All right. Now that I have common denominators, I can add the numerators. Y will equal positive 14 over 5. So once again, turn this into a coordinate. This should be 0, 14 over 5. This is the solution that you want to box. Why did I multiply by 5 over 5? Because I cannot add the 3 to the 1/5 unless the 3 has a common denominator. So the denominators must be the same before you add the numerators. Since I had a denominator of 1, I can't add that denominator with the -5. It needs to have the same denominator of 5. So that's why I multiplied by 5 over 5. That gives me 15 over 5. Now I have the same denominator, which then allows me to add the numerators. You never add the 5s. You never add the denominators. But you need them to be the same so that you can add the numerators. The negative is one of those that you have the ability to kind of move that one around. Dividing by -5 makes the fraction -1/5. So when it comes to fractions, if there's a negative anywhere in the fraction, it basically belongs to the whole fraction. Think about this, right? Like if you have 1 divided by -5, it's the same thing as saying -1 over 5. It's the same. So in terms of fractions, the typical kind of rule is that the negative typically belongs to the numerator. You don't really want to have a negative denominator necessarily. So when you're simplifying fractions like this can easily be just written as -1/5. Right? And then that allows you to focus on how do I then get common denominators, and then I can add the numerators, and you can see that the -1 plus 15, that can be done. Okay. Any other questions? All right, are we ready to try the last one? All right, let's do it. Last one here. Okay, let's begin with transformations. Try to keep them in order, in the correct order. What would be the first one? All right, let's start with the horizontal shift. Four units left. Okay, so pause right there. Horizontal shift, 4 units left. So where is your vertical asymptote going to be? It's going to be at x equals, and if you shifted 4 to the left, it's going to be at x equals -4. That's right? Because you moved it from x equals 0, you went 4 left, so your line moves to -4. All right. So if you wanted to, at this point, just state the domain. What's the domain going to be? Yeah, it's all real numbers except -4. Exactly, right? So the way we say that is all x such that x does not equal -4. Good, right? So after you do a horizontal shift, that takes care of your vertical asymptote and your domain at the same time. All right, what would the next transformation be? Let's go back to transformations. We already did the first one. This time I have 4. So what's the second one? I have a reflection across the x-axis. Okay, I could talk about that one, but even before that one, what else could be described? Take a look at the a value. Yeah, it's a stretch, right? So I have a I have a vertical stretch by a factor of 3, okay? As another common thing I'm seeing on the quizzes is you're saying that there's a stretch or a compression by -3. There's no such thing. The stretch is only by the value. It's only by the number. If you have a negative, it's because then it's talking about a reflection. So some of you are saying things like vertical stretch by a factor of -3. Technically, that's not correct. It's a vertical stretch by a factor of 3. Then there's a negative involved, so then you have to discuss the reflection. Okay, but you don't utilize the negative when you're describing the vertical stretch. Okay, because you're only looking at the size of the number. All right. Then the negative, then that one does discuss the reflection, but notice where the negative is at. I'm not sure why you guys are saying y-axis. A y-axis reflection would mean that the negative is the coefficient for the x. If the negative is next to my a value, what does that mean? It's an x-axis reflection, exactly, right? So reflection across the x-axis. And then finally, number 4. Okay, yeah. Yeah, if I was highlighting them in order, yeah. And then the last one, vertical shift 1 down, that's right. So vertical shift 1 unit down, right? So vertical shift 1 unit down. So you had a horizontal asymptote at 0. It shifts the whole function down 1 unit. So where is my horizontal asymptote going to be at now? Yeah, y equals -1. That's right. Whoops. And then you have a range. What would your range say? There you go, right? It's all of the y values as long as y is not equal to -1. So the set of y such that y does not equal -1. All right. Any questions so far? All right, so let's quickly just get through the intercepts. X-intercept, this is where we set y equal to 0. So we want y is equal to -3 over x plus 4 minus 1. I also want to point out on the homework, you're going to see the problems not with the negative in the numerator. You're going to see them kind of like right in the middle of the fraction. You're going to see them like this. What does that mean? That means the negative belongs to the numerator. Okay, so whenever you see it this way, it means this. All right. If they wanted you to know that the negative was in the denominator, then this is what you would see. And that's how you would know. It would be very obvious. They would put parentheses. I would put parentheses and a negative down there for you to know the negative is in the denominator. All right. But if you see it kind of like on the side, even with the fraction line, then that means that the negative belongs to the numerator. Okay? So if you see it either way, recognize it. Just know that it does not mean that the negative is in the denominator. When is it a reflection across the y-axis? If you saw it this way. because there you see that inside parentheses, in the denominator, the negative is the coefficient for the x. That's how you know it's a y-axis reflection. But if you don't see that, then it means the negative belongs to the numerator, and then that's a reflection across the x-axis. All right. So I'm just telling you, right, you might see it either way, okay? So either way, don't freak out. All right, so let's set y equal to 0. All right, so what do we do? First, you want to move the constant, set it up in a way where you can do a cross multiply. So let's add 1 first. 1 is equal to -3 over x plus 4. Right? Before you do the cross product, first the constant needs a denominator, and second, you need to wrap this in parentheses. Okay, because when you do the cross product, you're multiplying the entire expression, x plus 4 times whatever is on the diagonal. All right, so we're going to multiply 1 times x plus 4. So that means 1 times x plus 4, literally. And that's going to equal 1 times -3, which is just -3. So if I distribute 1, doesn't change anything on the side. That's just x plus 4 equal to -3. So if I'm solving for x, just subtract 4. X will equal -7. Right, so my intercept will be -7, 0. Yeah, I can show you in decimals. Let me finish the y-intercept first, and then we'll go look at the graph. Okay? That way we can look at all the pieces. All right, and then y-intercept real quick, right? This one means that we're going to set x equal to 0. So we have y is equal to -3 all over 0 plus 4 minus 1. So that gives us y is equal to -3 over 4 minus 1. And once again, you're in a situation where you cannot just subtract 1 minus, or -3 minus 1, because you need a common denominator. First, that denominator is 1. So 4 and 1 are different denominators. So you would have to multiply one of the fractions by a number to get it to be the same denominator. In this case, multiply by 4. So we can say -3 over 4 minus 4 over 4. And then what you're allowed to do is only subtract numerators. Leave the denominator as is. This will be 4 in the denominator. -3 minus 4 is -7. So you will have a y-intercept at 0, -7 over 4. All right, and there it is, right? So that's how you find all of the important pieces of information of the graph, and without having to graph it. Okay, any questions there?